Assalamu alaikum dear students. I hope you're all fine by the grace of Almighty Allah. I welcome you all to the 18th lecture of Thermodynamics 2. Lecture 18. The contents of lecture 18 are entropy generation for open system, derivation for entropy generation for an open system, entropy as rate equation, second law efficiencies, numerical problems, and conceptual questions and answer. Entropy generation for an open system. So here are some key points. Entropy generation, it is not a property of a system. So as we know that for specific entropy, when we are discussing regarding the specific entropy, we know that we can find the value of entropy at a specific state. Let's suppose a process is happening and let's suppose it's isobaric or isochoric process. So for a certain process, the process will move from state 1 to state 2. So we can find the value of specific entropy at state 1 and state 2 because specific entropy is the function of state and it's a property of system. Therefore its fixed value can be found out at the particular state. Therefore when you look into the property table, so you can find the value of entropy along with internal energy, specific volume, etc. So entropy generation, so entropy that is generated. So as you know that we have already discussed about entropy generation for closed system as well. So I have already told you about that the entropy generated during the process is only due to the irreversibility present within that process. So similarly for the entropy generation for an open system, it is also due to the irreversibility within the process. So the first point is it is not the property of this system. Entropy generation measures the extent of irreversibility. So let's suppose we have two states. So let's suppose we have process 1 is going from state 1 to 2 and there is another process line that is also joining state 1 to 2 and they have two dissimilar paths. So one has a frictional effect that are more in path 1. So the irreversibility for the process path of path 1 is greater than for the process path 2. Therefore corresponding entropy generation will be greater for that path. So the third key point is for reversible processes the value for entropy generation is 0. So as you know that entropy generation is due to the irreversibility, therefore for reversible process the value of entropy generation will be equal to 0. So now we will discuss about what are the mechanism of entropy transfer. So we know that there are two main mechanism of entropy transfer, that is heat flow or heat transfer or mass flow or mass transfer. So as you know that for an open system, so there is exchange of energy is also allowed and exchange of mass between the boundary and surrounding is also allowed. Therefore the two mechanism will be discussed during the this topic for entropy generation for open system. So as this is an open system, therefore there will be a flow, so mass will also be transferring in and out of the system, and heat will also be transferring in and out of the system. So we know that if heat is flowing into the system, then its entropy will increase, because as you can remember that the formula for entropy due to heat flow is given by S is equal to, or S gen is equal to Q by T. So Q represents the heat, the content of heat. So if the flow of heat is toward the system, or the heat is flowing into the system, then the sign is positive for Q. And if heat is flowing out of the system, then the sign convention we follow is negative Q, because the total heat content of the system is reducing. Therefore, when we say that the entropy of a system, or change of entropy, particularly saying change of entropy of the system is negative, that means the heat is flowing out of the system. So similarly, mass flow, so when, as you know that the second mechanism of entropy transfer is mass flow, therefore whenever a mass is entering into the system or mass is exiting the system, then there will always be an entropy generation term. So particularly for open system, because there is a change of mass, or mass is allowed to enter or leave the system, and there is energy interaction also. Therefore both of the mechanism for entropy transfer we will discuss in this topic. So note, entropy depends on initial and final state of the process, and hence called point function. So here you must distinguish between entropy generation and simple entropy or specific entropy. So usually when we are saying this about entropy, so we are usually discussing about the specific entropy. So I have already told you that the entropy depends on initial and final state, so it does not depends upon the path that followed. But entropy generation, on the other hand, depends on the path followed by the system. So the second point of is entropy generation depends on the path followed by the process, and hence called path function. So as we have discussed previously in previous lecture, that work and heat, so work and heat both are path functions. So as you know that pressure, volume, temperature, these are the property of the system or property of state. So they only depend upon initial and final state of the process. So along with pressure, volume, temperature, entropy or specific entropy is also a state property. So it depends on initial and final state. Whereas entropy generation is like heat and work, because it depends on the path followed by the process. So if the path that is followed has greater irreversibility effect, or frictional or other parameters that involve irreversibility, then the more irreversibility means more entropy generated. So entropy generation for irreversible process is always greater than 0. So because it is entropy generation is a term for irreversible process, therefore for irreversible process the value for entropy generation is always greater than 0. And entropy generation for reversible process is equal to 0, because there is no irreversibility present in the reversible process, therefore entropy generation term is 0 for reversible process. So there is a TS graph, so at state 1 and that is state 2. So there are two different paths are shown. So for path 1, that is also is the process from state 1 to 2, and path 2 is also shown another path for a process from state 1 to state 2. So both processes are going from state 1 to 2, but they both have different path. So let path 1 process has greater friction than path 2 process then. So here the frictional effect within the process that is changing from state 1 to 2 from path 1 has greater frictional effect, whereas path 2 has less frictional effect or less irreversibility. So path 1 has greater irreversibility and path 2 has less irreversibility. Then both processes are irreversible. So as path 1 has greater irreversibility, therefore the term entropy generation will have greater value for path 1, and path 2 that has less irreversibility will have less entropy generated term. Let's suppose the Sgen for path 1 is 5, then Sgen for path 2 is, let's suppose, 3, or will be less than 5, because path 2 has less irreversibility. So entropy generation depends on the path of the process. So as we have shown two different paths, so both have different value. For same initial and final condition, the value of entropy generation will be different for different process path. So here we have shown that for different path, because entropy generation is a path function, therefore for different paths the term or value of entropy generation will be different. So it will have greater value for the path that has greater irreversibility effect or frictional effect. So here a note is mentioned. So the first point is heat is a disorganized form of energy. We have already discussed about these four terms. So here I will only mention it for the revision, because entropy generation is directly linked to all these terms. So the first point is heat is a disorganized form of energy, and we know that entropy is arised or generated, or the term entropy is coined from the second law of thermodynamics. So the concept of disorganization of energy, we have discussed this in the second law of thermodynamics. So the term entropy is directly linked to that disorganization of energy. So whenever the term heat is mentioned, then there will be entropy term that is directly linked to that. Whereas work is an organized form of energy and work is not associated with the entropy. So I have uh, I have previously discussed all these 4 points in the previous lectures as well, but here I have mentioned them because for open system there is a heat interaction and work interaction, and within an open system there is an energy interaction between the system and surrounding. So that energy may be consist of heat or work. So that energy, then we have classified that energy interaction between heat interaction and work interaction. So when we will be discussing about heat interaction, then we will be considering the entropy generation term. Whereas when we will be discussing interaction of energy between system and surrounding in the form of work, then we will be neglecting the effect of entropy, because entropy is not associated with work. So let's suppose here we have a system. So boundary represent the control volume S this is an open system, therefore there will be an change of entropy due to mass flow. So there is a certain amount of entropy that is entering into the system and certain amount of entropy that is exiting out of the system. So let's suppose if we are discussing the same concept for the closed system, then the entropy, because in a closed system there is no mass interaction, there is the mass value is fixed, no mass is entering and exiting the system. So entropy is changed only due to heat interaction. But for open system, there is a continuous supply of mass within the system and the certain amount of mass is also exiting the system. Therefore, that mass flow represent the change of entropy. So here we have represented it with, you know that the S is the symbol represent entropy. So S in means that entropy is entering into the control volume, and S out means certain amount of entropy is exiting the system. So that entropy is associated with mass flow. So for steady state system, so we have already discussed about what are steady state system and what are non-steady state system in the lecture 9 and 10. Particularly we have discussed about non-steady state system. They are also known as transient flow system, and for time invariant system, or the system that does not change with the time, that are known as steady state system. So if we are discussing the concept of entropy generation for open system, that is for steady state system, then S in, so S in is the entropy that is entering into the system. So S gen is the term that represents the irreversibility effect within the control volume. So S generation or entropy generation, the second term, represent the irreversibility within the control volume, and S out is the entropy that is exiting the system. So if we kept the S generation term, entropy generation term on the left hand side, then on the right hand side we have left with entropy that is exiting minus entropy that is entering into the system. So their difference represent what is entropy generated within the control volume. So for unsteady state, so if the properties of the system are varying with time, so for steady state properties are fixed, so that is time independent. But for unsteady state, that is time invariant and that depends on the variation of time. So time dependent system for unsteady state. So we have discussed the transient flow or unsteady state process, in which we know that there is certain accumulation of mass within the control volume. So let's suppose if 5 kg of mass is entering into the system and 4.5 kg or 4 kg of mass is exiting the system, then there is a 1 kg of mass that is accumulated within the control volume. So as entropy is associated with mass flow, therefore certain entropy will be accumulated with the mass that is accumulated within the control volume. So for unsteady state, we have a equation or relation that is S in, that is entropy that is entered into the control volume. S gen, the second term that represents the irreversibility of the process within the control volume, minus S out, that is the entropy that is exiting the system, and ds by dt is the entropy term or rate of entropy that is accumulated within the control volume. So here if we want to calculate the relation or find out the relation for the value of entropy generation, so we have S out minus S in plus ds by dt. So entropy that is exiting out minus entropy that is entering plus entropy that is accumulated due to the accumulation of mass within the control volume. So here we have two main equations, one for the steady flow and one for the unsteady flow, to calculate the value of entropy generation for open system for steady state process and for unsteady state process. So the topic is entropy as a rate equation. So here you should remember that the rate means per unit time. So usually when we are discussing about heat transfer, so we usually take the term Q dot. So the unit for Q dot is kilowatt or watt or kilojoule per second. So that means the heat transfer per unit time. So when we are discussing about entropy as a rate equation, it means entropy transfer per unit time. So similarly, a control volume is shown here. So that control volume represents a system. So in the orange, that represents the system boundary. So M1 is the mass that is entering the control volume. S1 is the value of entropy that is entering into the control volume. Q1 is the amount of heat that is supplied to the system or control volume. So here control volume means the system. So M1 is the mass at inlet mass at the system, S1 is the inlet entropy, and Q1 is the heat supplied to the system. Whereas M2 is the mass exiting out of the control volume or system, S2 is the entropy that is exiting the control volume, and W is the amount of work that we have taken out of the system, that is supplied by the system. So W represents the work done. So here first we will discuss about for the unsteady flow. So for unsteady flow, as I have already mentioned, that there is a certain mass accumulated within the system. Therefore, the entropy term that is associated with that accumulation of mass is ds by dt. So that is a rate change of entropy per unit time. So here, to mass flow rate is multiplied with the inlet entropy. So to as you can remember that when we were deriving the steady flow energy equation, so first we have the equation that was multiplied by mass flow rate, and that has a value of capital Q, and its unit was kilojoule per second or kilowatt. Then we have divided that equation with mass flow rate, and the whole equation units was changed into kilojoule per kg. So here similarly the value unit of entropy are joule per Kelvin. When we multiply that with mass flow rate, so its unit is, that mass flow rate is kg per second, and its unit is joule per Kelvin. So and here we have Q dot by T. Q dot is kilowatt per Kelvin. So here M dot S has also the unit of kilowatt per Kelvin or kilojoule per second into Kelvin. So here S dot also represents the rate of entropy that is generated, minus W, because that minus is due to these terms are exiting. So M1 is the mass at the inlet, S1 is the entropy at the inlet, plus Q. Q is the heat supplied to the system. So the total heat content of the system is raising. Therefore, there will be a positive sign with Q because heat is supplied to the system. So the entropy term that is linked with the heat transfer is given by Q dot by T. So S dot gen is the rate of entropy generation due to the irreversibility present within the control volume. The negative sign represent that these properties are exiting out of the system. So minus is because work W dot is the work at the outlet plus m dot 2, that is the mass flow rate at the exit. S2 is the entropy at the exit. So when they both will multiply, they have the units of kilojoule per Kelvin. And ds by dt is the entropy or rate of entropy that is accumulated within the control volume due to the accumulation of mass within the control volume due to unsteady flow. Now for steady flow system, for steady flow system there is no mass accumulation within the control volume. Therefore the term on the right hand side that represent the entropy, rate of entropy due to the mass accumulation within the control volume is 0. So here ds by dt and here it is 0. So on the left hand side the value remains same, that is m dot 1 s1 plus q dot by t plus entropy generated minus w plus m2 dot s2 dot. So m2 and s2 are the mass flow rate and entropy at the exit, whereas m dot 1 and s1 is the mass flow rate and entropy at the inlet. And similarly q dot is the rate of heat supplied to the controlled volume. So on the previous slide you have two relation, one for steady and for unsteady state for the entropy generation, whereas in this slide you have entropy as a rate equation, so entropy per unit time. So here you have also for unsteady and steady state for entropy as a rate equation. So here is a new topic, that is second law efficiencies. So mostly that topic is usually discussed in the chapter of exergy. So here we will discuss this topic. So we will discuss what is meant by second law efficiency and why it is necessary to find second law efficiency. So second law efficiency is a measure of how much of theoretical maximum Carnot efficiency you can achieve, or in other words a comparison of the system thermal efficiency to the maximum possible efficiency. So you know that the Carnot cycle we have already discussed, the cyclic heat engine. So we have discussed the Carnot cycle. So we know that the Carnot cycle is based on 4 reversible processes, and the maximum thermal efficiency that can be achieved by any reversible heat engine can never be greater than the Carnot efficiency. So the value of Carnot heat cycle efficiency or thermal efficiency of Carnot heat engine is maximum. So for practical heat engine the value of efficiency will always be less than the Carnot heat engine efficiency. So second law is a measure how much the efficiency of the heat engine that is proposed or that is in the discussion has the corresponding we have a comparison between what is the efficiency of that heat engine that is under discussion and comparison with the Carnot heat engine efficiency. So the second law efficiency will always be between the Carnot and first law efficiency. So in time we will discuss what is first law efficiency and what is Carnot efficiency and how we will calculate second law efficiency. So here is a relation to find the second law efficiency. So eta and second 2i capital I or thermal efficiency of second, ठीक है. So to represent or to find how second law efficiency is calculated, so here is the relation. So second law efficiency is equal to actual thermal efficiency divided by maximum thermal efficiency. So actual efficiency is W actual divided by Q in. So here we have a practical heat engine. So in a numerator its actual efficiency is calculated, whereas in the denominator it is multiplied by the efficiency of Carnot heat engine. So because maximum efficiency or thermal efficiency maximum is can only be achieved by Carnot heat engine, so it is a ratio. Second law efficiency is the ratio between the efficiency of actual heat engine divided by maximum thermal efficiency. So actual efficiency is calculated by W actual divided by Qn, and thermal efficiency maximum or Carnot heat engine efficiency is calculated by W max divided by Qn. So Qn will be cancelled out and the term left is second law efficiency is equal to W actual divided by W max. So maximum work is obtained by only reversible heat engine, therefore W max is changed with WREV, that represent work output of a reversible heat engine. So this relation is for work producing device, and on the right hand side we have another second law efficiency relation for work consuming device. So let's suppose if we are discussing about heat engine and we have to find the second law efficiency of any heat engine, then we will use that relation on the left hand side that are in blue color, and on the right hand side the color of the relation or equation are purple. So for work consuming devices like we are discussing about refrigerator, heat pumps, then we will be using the relation that are on the right hand side that are in purple color. So here we have W reversible on the numerator side and W actual in the denominator. So for work producing, W actual is in the numerator and W reversible is in the denominator, whereas for work consuming device W reversible is in the numerator and W actual is in the denominator. So these are opposite. Similarly, if we have coefficient of performance, so we will have coefficient of performance of actual device on the numerator and coefficient of performance of reversible device or Carnot refrigerator we have in the denominator. Coefficient of performance of reversible device in the denominator. So here we have a example problem. So we have in the two different schematic diagrams we have shown two heat engines. So here on the left hand side it is heat engine A, and on the right hand side we have heat engine B. So first we will discuss how heat engine A is constructed. So the source temperature for heat engine A is 600 Kelvin, and the sink temperature for the heat engine A is 300 Kelvin, and work output of heat engine A is 30 kilojoules. So the heat that is absorbed by heat engine A from source is 100 kilojoules, and heat that is rejected by heat engine A is 70 kilojoules. And for heat engine B, the source temperature is 1000. So for heat engine A it was 600, and for heat engine B the source temperature is 1000 Kelvin. The same amount of heat, 100 kilojoule, is absorbed from source into heat engine B, and 30 kilojoule of work is produced by heat engine B, and 70 kilojoule, that is same amount for B and A, has same amount of heat that is rejected into the sink, that is also at 300 Kelvin. So you can see, compare that only the source temperature of heat engine A is less than heat engine B, whereas all other parameters are same. Look at, you see that QH of 1 is 100 kilojoules, and QHB is also 100 kilojoule, QLA is 70 kilojoule, and QLB is 70 kilojoule, and WA and WB also equal 30 kilojoules for both, and only difference is the source temperature. So now we will know, after solving this example, we will be able to comprehend why the second law efficiency is important. So you should remember that the properties of heat engine A and B are all similar, except that the source temperature of heat engine A is less and heat engine B is greater. So when we are calculating the thermal efficiency of heat engine A in accordance with the first law of thermodynamics, then the efficiency comes out to be 30%. So efficiency is W over Q. So 30 over 100, that is 30%. And on the right hand side, we are calculating the thermal efficiency of heat engine B in accordance with the first law of thermodynamics. So similar, Q thermal efficiency is W by Q, 30 by 100. So thermal efficiency of heat engine B is also 30% for in accordance with the first law of thermodynamics. Note, we cannot check the performance of any engine based only on the first law of thermodynamics. We must check the performance in accordance with the second law of thermodynamics as well. So in the previous slide we have two different heat engine, but they have similar parameters. So QH and QL and W work output for both engine was same, but the source temperature were different. So heat engine A has less source temperature and heat engine B has greater source temperature. But when we have checked the thermal efficiency based on first law of thermodynamics, that is same for both heat engines. Now we will check the thermal efficiency according to the second law of thermodynamics. So what is the procedure? So from second law of thermodynamics, the maximum efficiency, so if we have changed or replaced with the heat engine A is replaced by a reversible heat engine, then it has the maximum efficiency. So let's suppose heat engine A is a reversible heat engine, then it will have maximum efficiency. So to calculate the efficiency of reversible device, the formula is 1 minus T 2A over T1A or TL over TH. So maximum efficiency for heat engine A is 50%. So when we were calculating the thermal efficiency according to the first law of thermodynamics, it came out to be 30%. But when we are calculating thermal efficiency according to second law of thermodynamics and considering that the heat engine is a reversible heat engine, then the efficiency comes out to be 50%. Now how to calculate second law of efficiency? To calculate second law efficiency, we will be dividing the actual thermal efficiency with the maximum thermal efficiency that can be achieved. So we will divide 30 by 50. So the thermal efficiency comes out to be 60%. So 30% is the thermal efficiency that we have calculated according to first law of thermodynamics, and 50% is the thermal efficiency that we have calculated according to second law of thermodynamics and considering that the heat engine is a reversible heat engine. And then we have taken the ratio of actual efficiency with respect to the maximum thermal efficiency. So second law efficiency for heat engine A is 60%. Now we will be calculating the second law efficiency for heat engine B. So eta max B. So now we are considering that we have replaced the heat engine B with a reversible heat engine. So the relation to find the efficiency for the reversible heat engine is 1 minus TL over TH. So here TH is 1000, and for heat engine E the temperature of source is 600, and in heat engine B the temperature of source is 1000. So maximum reversible thermal efficiency for the reversible engine is 70%. So here that's how we have calculated. So now to calculate the second law efficiency for heat engine B, we have the relation efficiency of B divided by maximum efficiency of B. So 30 is the amount, 30% is the thermal efficiency that we have calculated according to first law of thermodynamics, and 70 is the value of percentage efficiency that we have calculated according to second law of thermodynamics and considering that heat engine B is a reversible heat engine. So to calculate second law efficiency for heat engine B, we will take the ratio of actual efficiency and maximum efficiency. So second law efficiency for heat engine B is 42%. So now you know that second law efficiency tells the difference. So for heat engine A it is 60%, and for heat engine B it is 42%. So second law efficiency is very important because it also incorporates the source and sink temperature as well. So in heat engine A it is producing the same amount of work, whereas the source temperature is 600 Kelvin, and heat engine B is producing the same amount of work, whereas the source temperature is 1000 Kelvin. That means the heat engine A is more efficient than heat engine B because both are producing same amount of work, and the source temperature for heat engine A is 600 and heat engine B is 1000. So we have to supply more energy to maintain the source temperature, and the efficiency for heat engine B is less than the heat engine A. So This is statement of third law of thermodynamics. It states that the entropy of a perfect crystal is zero when the temperature of crystal is equal to absolute zero. So that statement, we have already discussed that statement in the previous slides as well. So at that time I have asked you to search what is meant by a perfect crystal. So here is the one line definition. A perfect crystal, the atoms and molecules of the crystal are arranged in organized way. It is impossible to lower the temperature of any subsystem to absolute zero. Absolute temperature is only theoretically possible, therefore absolute zero entropy is also theoretically possible. So here in the statement is said that at 0 Kelvin temperature, absolute zero temperature, the entropy is zero. As to achieve absolute zero is only theoretically possible, therefore to attain zero entropy is also only theoretically possible. So here is a conceptual question. A reversible process in a piston cylinder is shown. Indicate the storage change U2 minus U1 and transfer of work for 1 to 2 and transfer heat 1 to 2 as positive, 0 or negative. So here is the reversible process piston cylinder is shown. So these are the two PV and TS diagram are shown that represent a piston cylinder process. So you are asked to indicate whether the U2 minus U1 term or work and heat transfer are positive, negative or zero. So as piston cylinder is a closed system, so the relation for work done is integration P dV. So here from 1 to 2 as volume is increasing, so as volume is increasing, so dV is positive, therefore the value of W1 to 2 is also greater than 0. So on the second, to calculate heat transfer, so for Q1 to 2 integration T ds, so as ds it is an isentropic process shown, so value of entropy is constant, therefore ds is 0 and Q1 to 2 is also 0. So to calculate U2 minus U1, we have first law of thermodynamics. So by energy equation, U2 minus U1 is equal to Q1 to 2 minus W1 to 2. So as the first term Q1 to 2 is 0 and W1 to 2 is positive, but when it is multiplied with the minus sign, that means the value of U2 minus U1 is less than 0. So the second conceptual question is, carbon dioxide is compressed to a smaller volume in a polytropic process with N is equal to 1.4. How do the properties internal energy, specific enthalpy, specific entropy, pressure and temperature change? So these are 5 properties. We have been asked to check whether these properties will increase, their value will increase, decrease or remain constant. So for carbon dioxide we have table 1 A.5. So the value of K is mentioned is 1.289. So for polytropic process the value of N is greater than K. So K in book you should remember, sometime it will be written gamma or K, so it is the value of adiabatic index. Similarly for air the value of N is 1.3 and for gamma it is 1.4, but for carbon dioxide the value of N is 1.4 and gamma or kappa that is adiabatic index is 1.289. So n is greater than k and the process curve is given in the figure. So we have PV diagram and TS diagram. So we see the value of pressure. So the process is moving from right to left. So here it is represented state 1 and at state 2 the pressure is increasing and volume is decreasing. So we see smaller volume means moving to the left in PV diagram and thus also increase in pressure. So when we are seeing the TS diagram, then the temperature is also increasing and entropy is also increasing. So here we will see that pressure is increasing, volume is decreasing, temperature is increasing, entropy is also increasing, and enthalpy H is equal to U plus PV. So as internal energy is increasing, therefore enthalpy is also increasing. So the question is, when a substance has completed a cycle, specific volume, internal energy, specific enthalpy and specific entropy are unchanged. Did anything happen? Explain. Yes, during various parts of the cycle, work and heat transfer may be transferred. That happens at different pressure, temperature. The net work output equals the net heat transfer in energy conservation. So dependent upon the sign, it is a heat engine or heat pump. So it may be a heat pump or refrigerator. The net effect is thus a conversion of energy from one storage location to another, and it may also change nature. Some Q or heat transfer was changed to W or work done or the opposite. So if it is a closed cycle or cyclic process and volume, internal energy, enthalpy and entropy are not changed, then the value of work done must be equal to the amount of heat that is supplied. So here it is written that the heat transfer happened at different temperature and pressure. So net work output is equal to the heat transfer. So some amount of Q, the heat is transferred to the system, and it is equal to the work that is deduced from the system. Let's suppose 15 kilojoule of heat is transferred to the system. So the pressure and temperature are changed, but work is taken out of the system, therefore the other properties are remain constant. Assume a heat engine with a given QH. Can you say anything about QL if the engine is reversible and if it is irreversible? So for a reversible heat engine, because it's cyclic process, Q by T is equal to 0 and QH over TH minus QL over TL. So as TL is lower than TH, then QL must be correspondingly lower than QH to obtain the net zero integral, because dQ by T for the cyclic process, the value of entropy, because the entropy is a state function for the cyclic process, similar to internal energy, the value of entropy will be equal to 0. So as TL is less than TH, therefore QL must be less than QH, because as their ratio, until their ratio is same to, so their net effect is 0, so the ratio of QH over TH must be equal to the ratio of QL over TL. So for an irreversible process, so there must be an entropy generation term, and for the cyclic integral term for dq by t must be less than 0. Therefore, QH over TH minus QL over TL. So this means that QL is larger than before given QH and TH, because let's suppose the ratio of QH over TH is 3, and then QL over TL will also be 3 in the for reversible process. But in the irreversible process, because that the net effect is less than 0, therefore the value of QL must be greater than, or TL must be less than the in accordance or in comparison with the first one. So the same is written, that means QL is larger than before given QH and T. The irreversible heat engine rejects more energy and thus gives less work out. So irreversible heat engine, it will give less work and consume more energy. So the third conceptual question, why do we write del S or S2 minus S1 whereas we write integration dq by t or S1 to 2 generation? So the short answer is S1 to 2 is the path function and they are our state function, therefore we write it in these ways. So you can read the answer as well. The first part of the change in the storage S2 minus S1 of entropy in the mass, and the second part is the transfer or generation during the process from 1 to 2, because that is a heat entropy transfer due to heat, and that is the entropy generation due to irreversibility. The storage term corresponds to the left hand side of the balance equation. For entropy, the integration dq by t represent a transfer of entropy across the control volume surface during the process from 1 to 2, and S1 to 2 generation express the total amount of entropy being generated inside the control volume, and both are on the right hand side of the balance equation. So S2 minus S1, usually write this on the left hand side. So these S2 and S1 are the state properties or specific entropy at state 1 and 2, and dq by t is the value of entropy transfer due to heat interaction, and S1 to 2 is the value of entropy that is generated due to the irreversibility within the process. So here is the home assignment that you should all go through example problem of each topic discussed during the lecture. You should write a handwritten summary report must be submitted. So as discussed in the online session as well, for the all the lecture of entropy related, so as this chapter is concluded in this lecture as well, so you will write a single lecture summary report for these topics. So all students are advised to keep hard copies with them, and if the scenario permit or circumstances permit, and if the university is open, then we will be taking these hard copies as well. So all students are advised to prepare previous lecture thoroughly, so there may be a viva or oral question answer session, and you may be asked question related to the topic discussed in this lecture. So take care. Allah Hafiz.